Okay, so this is there, but now we will add another axiom, okay, that the velocity of light c is constant in all inertial frames. Okay, so these are the two postulates of special relativity. Okay, so this is the addition. This is the only addition we have in special relativity. Okay, now we have to see with this addition can we resolve what kind of transformations we get, and can we resolve the problem which was occurring in Galilean transformation. Okay, so what do we mean by velocity of light? Velocity of light c remains constant in all frames. Okay, so consider two frames k and k prime. Okay, and at instant t, at t equal to 0, okay, these two frame origin of k coincides with origin of k prime. Okay, and the axes are, the frames are arranged in such a way that these respective axes are parallel to each other. Okay, so I'm not drawing the frames. I'm not showing the k and k prime frames. Okay, so now let us consider any point. Let us consider a point. Consider 2 points. Okay, say p1 in frame k. Let us consider 2 points p1 and p2. So p1 is labeled by t and vector x, and p2 is labeled by t, say sorry, t1 x1 and t2 x2. Okay, and suppose our experiment is sending a light signal from p1 and receiving at p2. Okay, so these are the two events. Okay, event 1 is sending the light signal from point p1, which is labeled in k frame as t1 x1, vector x1, and receiving the same light signal at point p2, which is labeled by coordinate t2 and x2, vector x2. Okay, fine. So since light wave travels with velocity c, okay, we have the following equation. Okay, so it is x2 minus x1 whole square. When I write x2 minus x1, these are the vectors. Whole square means this dot same quantity. Okay, this is equal to c square t2 minus t1 whole square. Agree? This is the equation of spherical wavefront. Okay, fine. So this implies, we can write it in we can take this here, and it is x2 minus x1 whole square minus, so maybe I will write in this way, minus of this plus of c square t2 minus t1 whole square is equal to 0. Fine. So this is the equation of spherical wavefront. Okay, this is the difference. This is the distance traveled. Okay, and this is the radius of the spherical wavefront. So this must be equal to this. This is what it says. Okay. So now if I'm, so I will keep the two events same. P1 and P2 are same, but I will just label them differently. So now let us see in K prime frame. So K prime frame, my event P1 is labeled by T1 prime and vector x1 prime, and this event P2 is labeled by T2 prime and vector x2 prime. Okay, because this velocity of light c is same in this frame also. Okay, we will have the similar equation with unprime variable replaced by prime, but this c will remain same. Okay, so this we can write in this frame, we have c square t2 prime minus t1 prime whole square minus x2 prime minus x1 prime whole square is equal to 0. Okay, so in both the frame we have the spherical wavefront. Okay, this is in K frame, and I don't know yet what is this, how these primes are related to unprime, but they should be related in such a way that if this is true in K frame, then this is true in K prime frame. Okay, so now let me denote. Okay, suppose if I call interval, suppose if I define the quantity interval between two events. Okay, so, suppose if I define a quantity interval between two events, say one event 1 and event 2 by say s12. Okay, then this is by definition is the square root of this. Okay, it is the 4, you can see it is a 4 distance, or I will say it is s12 square is nothing but c square t square t2 minus t1 whole square minus x2 minus x1 bracket whole square. So this by definition is 4 distance square. So it is like a distance in 4 dimensional space, but with very important difference, there is a minus sign here. Okay, so I will say the interval between two events, I will define the interval between two events by this quantity. Okay, sometime we say s square as interval, or s12 square as interval, or s12 just as interval. So it's just a question of taking square root. Okay, so this is the interval between two events, this P1 and P2. Okay, in K frame. Okay. So for light wave, this interval, this is 0 for light wave. So if the intervals, if the events are such that sending a light signal from T1 x1 and receiving at T2 x2, then this quantity is 0. That is what we have seen here. Okay, so equation, this box and this box precisely says that. Okay, that this interval is 0 if your events are like that. Okay, events are that sending the signal from one point and receiving it at other point. Okay, fine. So this is the definition of interval. Like the definition of distance in your R3 in three-dimensional space is just square root of this quantity, square root of this quantity. Similarly, I define the distance between two events as this. Okay? And I will call that distance, sometime I will call this as interval. Okay. Now, but this is the statement about the light signals. Okay. So now let us generalize this. Okay. Suppose my events P1, T1 x1 and P2, which is T2 x2 are infinitesimally separated. These are infinitesimally separated events. Okay, it means that the distance between them is infinitesimal, spatial distance. Okay, and obviously they are also infinitesimally separated in time also. So we will have infinitesimal interval that I am writing as ds square, which is c square dt square minus dx square, vector dx square. Okay, where this dx is defined through your limiting procedure. Okay. Okay, it is defined through your limiting procedure. Okay, when point 1 approaches to point 2. Okay, so two infinitesimally separated events, for two infinitesimally separated events, the interval is given by this expression. Okay, is it clear? So this is happening, everything is happening in k frame. Okay, and note that here, okay, I have not assumed that these two events are concerning about the sending light wave and receiving light wave. Okay, these are general events. Okay, so now given the constancy of speed of light, what can we say about this ds square in two frames? Okay, one thing what we have seen is the following. We have seen that when speed of light is constant, then in two frames the equation of spherical wavefront is remains same. Okay, they satisfy the interval, the for the light wave, the interval between two events satisfies these two equations. Okay, clear? So what we have first, we have ds or ds square equal to 0 for uh, uh, for uh, light signals. Okay, so the interval between two events is 0 for light signals. Okay, and second observation is, what is the second observation? We should note that these two, when these two events are infinitesimal, okay, that means see this ds square, okay, this is infinitesimal, the left hand side is differential. Okay, so if I take the square root, okay, I will get a differential of order dt and ds and dx, right? When I take the square root, what will be ds? Ds will be square root of c square dt square minus dx square. Okay, so this is the differential of order. When I take square root, it will be a differential of order dt and dx, right? That means it is a first order in change. Okay, is that clear? And if these two events are if these two events are about the light sending and receiving the light signal, then ds equal to 0. This is what we have. Okay, so the second thing is,
Sir,
yes,
can you explain the first observation for light? What does for light signals mean?
light signal we have discussed, right? For light signal, this interval between two events is essentially 0,
But
right?
what are the two events?
Two events is sending the light signal and sending the light signal at p1 and receiving it at p2. If this is my two events, these are my two events, then the four distance or the interval between two events is essentially 0, because this is how we define it, right?
Okay,
Okay.
at when I am at P2, when I receive the light signal, I will say that for me the P1 has happened at that same time. So that is
No,
why
no, not time. See, the events is labeled by T1 and X1. Second event is labeled by T2 and X2. Okay, these two are different points in space time. Okay, my event is sending the light signal from T1 X1, and second event is receiving it at T2 X2. The way we defining two intervals is the four distance between two events, that is defined like this. Once I define this, then I say that the interval between light signal is always zero, right? Clear? Because this is our interval.
but
This
then
is the,
why have we defined it like this?
it has some special significance. That's why. Okay. See,
Sir,
this is the distance. This has nothing to do with the distance as it stand. Okay. Now we are defining this quantity, the left hand side quantity, as the interval between two events. Okay. So essentially, for 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 light signal, this must be equal to zero. That represents the two events are, one of them is sending the light signal and another must be receiving the light signal. That's it. That means it is concerning about the light waves.
sir,
Hmm?
here ds is equal to 0 for both the frames, right?
Delta is, yes, S12 square. Here I am not talking about the infinitesimal separated events. These are general. These two are the 2 points in space time. Okay, these are the 2 points in space time. Okay, one is labeled by T1 X1 and another one is labeled by T2 X2. Okay, and here I am sending the light signal and here I am receiving it. That's it. These are two events. Okay, these are not infinitesimal separated. In general, your light signal satisfy this. Is that clear? Okay, now I defined my interval between two events like this. Okay, clear? So I'm defining distance in four-dimensional space. Hmm? That is c square t2 minus t1 whole square minus x2 minus x1 whole square. Okay. The moment I define this, then for light signal, this I will say that S12 is always zero. Now, even if that statement then hold even for infinitesimally separated events, hence ds is equal to zero for light signals. No special statement. It is not such a big statement. Okay, it's simple, right? It is a spherical wavefront. It satisfies the equation is given by this. I am now calling this as the interval between two events. Hmm? Okay. Now, what is special is the following. Okay. So we have two things: ds equal to zero for light signal, and ds obviously if this is zero, then obviously you have ds prime is also zero. Okay, and the second observation is that, see, these are the these are the differentials of same order, right? These are the in k frame, ds is a differential. Okay, differential in dt and dx. Okay, so there is a addition. Okay, so I have, or what is the order of this differential? Ds. Okay, it is the first order in dt, first order in dx. Okay, yeah. When I go to other inertial frame, okay, k prime. Suppose that k prime frame is moving with velocity v. What we can expect about this nature of the differential? We should expect that ds and ds prime should be of same order. I don't know what is the relation between them, but we expect that these two should be of same order. What do I mean by that? If ds is of first order in dt and dx, okay, ds prime will be an interval of the same two events seen from k prime plane. Okay, so if I want to write expression for ds prime, what it will look like? It is the interval between two events seen from the k prime plane. So it will satisfy similar equation, but prime replaced by unprime. Sorry, unprimes are replaced by primes. Okay, clear? So there is a prime here. Okay. So
Are we imposing the condition of homogeneity and isotropy using
no, no,
this?
no, 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 not yet. Not yet. I have not yet. I'm not building yet the relation, right? I'm not. I have said nothing about how ds and ds prime are related. This is ds. This is the ds written in k coordinate system. This is the interval written in k prime coordinate system. The order of the differential is same. That means it is the first order in dt prime and dx prime. This is the first order in dt and dx. That's it.
Okay.
Okay. Now, now I want to make a relation between how this ds and ds prime should be related to each other. Okay. Remember, ds is the infinitesimal interval in k frame. Ds prime is the infinitesimal interval between two same events in seen from k prime frame. Okay, so now how this question is how these ds and ds prime are related to each other. Suppose ds prime, let us assume that ds prime, just a minute. Suppose my ds prime square is equal to some function of ds square. Okay, and we need to determine what is this function. Okay, now this first condition tells us what? If ds equal to 0 for light signals, if ds equal to 0 in one frame, then ds prime equal to 0 in another frame. So whatever we are writing, it should hold for light signal also, right? Okay, it tells us that there should not be. Okay, so let me erase this first, write it in slightly different form. Okay, in general I can write this as some function of ds square. But this should not, this first condition tells us that this must involve some multiplicative factor. This function should be such that, okay, it will involve some multiplicative function times ds square. Okay, there should not be any additional terms independent of ds. Why? Because if ds equal to 0, then this term goes to 0, but this will not, right? So if there is such a term, then it should also come with ds square. Agree? There should not be any additive factor. Okay, is that clear? So that I'm writing in a shorthand notation by this f of ds square. Okay, clear? Fine. Okay. So this first condition tells us that there should not be any additive factor. Okay. And the second condition tells us that this must be of this form. So let me, I have already written it, but this must be of this form. This function must be of this form. It may depend on your dx, it may depend on your dt, it may depend on what is there, your velocity between two frames and ds square. Okay, it, this is what we must have. to satisfy these two conditions. Okay, first condition, because of first condition, there should not be a term like this. Okay, and because of the second condition, sorry, yeah, yes, let me see. Yeah, so yeah, so from the first condition, there should not be any additive term. Okay, and the second condition tells us that if it is ds prime square, then here also it is ds square, because order of differential should match. Okay, so this is what we can say in general. Okay, this function, okay, may depend at this step. This function may depend on your dx, vector dx, dt, and velocity vector. But now your space and time, you apply the homogeneity. Okay, the space and time is homogeneous. What it tells, okay, it tells that in, suppose I have coordinate system k, okay, and if I take say rod, okay, so I'm explaining the homogeneity in space. A similar argument holds for homogeneity in time. Okay, suppose if I take a rod and measure its distance here, okay, and if I take same rod and measure its distance here, okay, around, so suppose this is infinitesimal rod and this is also infinitesimal rod. These two are same rods. Okay, first I measure distance about point say x, and suppose afterwards I measure it about say point x2. This is x1 and this is x2. Okay, obviously the distance between this end to end distance of this rod is same, whether you measure it here or whether you measure it here, or whether you measure somewhere, so some other point. Okay, clear? Okay. So distance between two points is same whether you measure it, the measurement dx, whether it is been done at about point x, x0 or x1 or x2, it doesn't matter. Okay, that is your homogeneity of space. Similarly, there is a homogeneity in time. Okay, with, so your interval, okay, should not depend on where you are measuring these two events, about what point you are measuring. Okay, yeah. So this means that this function should not depend on this. Okay, so this function only depend on, it may depend on velocity only. Okay, this is what we have. Is it clear? Now here also we can simplify further. Okay, here the velocity vector is coming. Okay, but again, because of this vector nature, the direction is coming. Okay, but a priori no direction is favorable, right? There is no, we should not assume that the z direction or y direction or velocity vector direction, okay, that this direction should not come into the picture, okay? Because that is not what we have assumed.
Sir, excuse me.
Hmm?
Sir, this v is the speed of that means from one event to another, which is whatever it's going. Is that, or is the relative velocity between the two frames? V.
No, relative velocity. Relative
Yes,
velocity.
sir. Okay.
It is a frame k prime. It is frame k and it is frame k prime. Okay.
Yes, sir.
This is a frame k prime. Okay. What we have, I want to determine what is this function. Okay. So at the to begin with, this function may depend on your where you are measuring. Okay, these events, that is dx and dt. Okay, and velocity. in general it depend on velocity vector, but because of the homogeneity of space and time, it will not depend on your dx and it will not depend on your dt. Okay, it will not depend even on magnitude of dx. Okay, because magnitude of dx will tell us, again same argument, your homogeneity says that it will not depend on dx. Okay, so it is both in magnitude as well as in direction. Okay, so at this step it depends only on the velocity vector, but again because of the vector nature, okay, we are creating unnecessary bias towards one direction, so it should not depend on the direction. Okay, so at so ultimately this homogeneity of space, and the second argument is uh, the isotropy of space. Isotropy means all directions are same, equally favorable. Okay, homogeneity and isotropy says that this function f dx dt. In fact, I can write dx prime and dt prime also. Okay, here. But why I'm not writing dx prime and dt prime? Because this is, see here I am not writing dx prime and dt prime. Okay, because then the differentials will be different. Order of the differentials will be different. Okay, but you can put that and argue that it should not depend on dx prime and dt prime also. Okay, so this function f of dx dt and v must be of the following form only: magnitude of velocity. Okay, so at max your ds prime square must be equal to f of vector v ds square. Now it satisfies all the criteria. Okay, so if ds for light signal, if ds equal to 0, then ds prime equal to 0, and these two are differentials of same order. Okay, velocity is not differential, velocity is just a constant, your constant relative velocity. When I write magnitude, I should say speed. Okay, clear? So this is what we have. So let me write this in slightly different notation. Instead of f, I will write lambda of, okay, clear? So this is how interval in one frame is related to interval in another frame when two frames moves with constant relative velocity. Okay, but now same, so there is no uh, we should not give any importance to k frame over k prime frame, right? That means similar statement must hold if I go from prime frame to unprime frame in reverse way. Okay, that means ds square, if I want to write the expression for ds square, then what should I have to write? There must exist inverse transformation, okay, which will also depend on same arguments will hold. Okay, but that is for inverse transformation. Okay, it should depend only on the magnitude of velocity and then ds prime square. Okay, so this is from k prime to k prime frame, and this is from k prime frame to k frame. Okay, inverse transformations. We demand that inverse transformation must exist. Okay, because there is no if I do not assume that, then there is something special about k frame. Okay. Okay, so this inverse exists means there must exist some function lambda inverse which also depends on magnitude of the velocity. Is that clear? Okay. Now if I consider a frame k frame, okay, I can talk about going from k frame and coming to k frame. Okay, that means what? No relative, just one single frame going from k frame and coming to k frame. Okay, it means that ds square equal to lambda 0 ds square, right? That means it is identity, no change. Okay, I am not going to any other frame. I have one frame. I am just saying that I am going from k frame and I am coming to k frame. Going from k frame to k frame, you can say. Okay, that is given by this expression. Agree? So this tells us that lambda 0 must be equal to 1. Similarly, lambda inverse 0 must be equal to 1. Okay. Now ds, it also says that suppose if I use these two equations, okay, this equation and this equation, okay, I will get what I am going to get. If I use these two equations, ds prime and ds prime square and ds square, then I will get lambda magnitude of v, okay, into lambda inverse magnitude of v must be equal to 1. Okay, this is how we define the inverse function. But what is this? What would be this inverse function? We have k frame here and we have k prime frame here. Okay, clear? What to go from k prime frame to k frame? What we must do? Remember this Galilean transformation. We are just changing the direction of velocity, right? Okay, v goes v. If I replace v by minus v, I can achieve the same effect. I can go from k prime frame to k frame. Okay, clear? So it means this equation will translate into following. Okay, lambda magnitude of v, okay, into lambda inverse should be what? Lambda inverse of mod v must be equal to lambda of, agree? Inverse means you are changing the direction of velocity. Clear? So lambda v, lambda of mod v minus mod v must be equal to 1. But this is just same. Okay, it means, this means that your lambda square of mod v must be equal to 1. But then I have lambda equal to plus 1 or minus 1. But minus 1 is overruled because of this. Okay, so lambda of mod v must be equal to 1 only. Agree? So if I demand these two conditions, if I demand these two, okay, and if I demand the existence of inverse, then I left with this only. Okay, which is nothing but, which is one way of saying ds prime square is equal to ds square. So event in two frames, the infinitesimal distance between two events in two frames remains unchanged. This is because of what? Because of constancy of light. Okay, this is the essence of your this postulate, two postulates. Okay, one is already there and the second one is constancy of light. Okay, so when we impose the constancy of light, we get the interval invariance of interval between two events. Okay, in frame k and frame k prime. This is what we get. Okay.
So we have assumed the order of differentials are similar in both the frames. It's same. So what is the
Yes.
logic behind that? And how can we
No,
take this?
because it is distance, right? ds prime is ds equal to what? ds equal to dt dx. It is the first order in dt and dx. Okay. In prime frame also, in prime frame also, it is just a minute. Huh? Just a minute. Just a minute. Yeah. So what was your question? Question was why this order of magnitude order of differential should match? No, this is
Yeah.
ds is the four distance in k frame. ds prime is the four distance in k prime frame. Okay, so in k prime frame, how it should behave? It should behave as a first order in dt prime and first order in dx prime. That's it.
Just we are saying this is a distance. That's why I mean it has to be distance in some kind of
Yes,
distance in
yes,
another frame.
yes. So the order of
Okay.
differential order of dt and dt prime must be same. Okay.
Okay. Okay.
Okay. So this is what we have by demanding the constancy of light.
So,
Yes.
if the transformations were not linear, like x dash equals to x minus bt, so the order of x dash and x are same. So if they were not same
Yeah.
in ds and ds, it would not be same, right?
No, it would not be same. But that will not be. Then we are not talking about the inertial frame.
Yes, yes, right.
Okay.
Yeah.
So if interval in one frame is ds, if suppose if it is some number, then that number should not change. If you go to any other inertial frame. Okay. Is that clear? Okay. So remember now what is recall what is your ds. Ds is c square dt square minus vector dx square, that must be equal to c square dt prime square minus vector dx square. And this is, we have already shown this for light signals, but this is in general true now.
Sir,
Okay.
in the RHS of the equation, there should be dx prime square, right?
Yeah, dx prime. So it is the prime. So maybe I will end up. It is, there is a prime. There was a prime. Okay. Okay. Fine. So just by demanding the, just by making the extra assumption about the speed of light, we have we have this extremely important result. Okay, and that changes everything. That changes your known classical physics. Okay, your instead of, okay, let us go back to your R3. Okay, in R3, okay, we usually say that the distance between 2 points, okay, say origin and say point P in R3, suppose if R is the distance between these 2 points, should not change if I rotate this frame, right? If I consider rotation of this frame, say this is my K and this is my K prime, and this is some kind of rotation, then the way we define rotation is the following. We demand that this distance between 2 points, in other words, this R should not change in K and K prime frame. So my rotation is a transformation which keep distance square. So vector r square must be equal to vector r prime square. Okay, this is how I define my rotation. This is how I define, how I classify my rotation transformation. Okay, similarly here I have a transformation which keeps unchanged, which keep intact this quantity. This quantity remains unchanged. Okay, under that unknown, some unknown transformation. Okay, so if I demand the invariance of this quantity, it means that I have taken into account, I have already taken into account constancy of speed of light. Okay, so this is the analogous statement for rotation in 3D. Okay. So you can also view, in fact this is what we are going to do, you can view the transformation between two frame as rotation in tx plane or ty plane or tz plane.
Excuse me, sir.
Yeah.
Sir, I'm going a little ahead, but sir, in the Minkowski's matrix form, that Minkowski matrix determinant is actually not constant. So how come
Why
it
not
is
constant?
root?
It is constant, right? Why not it is constant? It is constant. So in Minkowski metric, it is this. Why not it is constant?
Sir, but that omega factor, that gamma factor, sorry, that gamma factor is dependent on the relative velocity
No,
between
no,
the
but
frames.
in the
So
metric it does not depend, right? There is no velocity in metric.
okay,
Metric there
okay,
is no velocity, right? Correct?
yes, yes, sir, yes.
So now, okay, okay. Now let us ask another question. Now, the question number one is: can we construct a frame in which two events, okay, in which two events, let me see the order. Two events two events occur at the same point, same spatial point. Okay, so look at this question. The question is: can we construct a frame in which two events occur at the same spatial point? That means it is assumed that we have two events. Suppose I have K frame, okay, and in K frame, let us consider two events, okay, T1, X1, okay. Okay, before going into this question, this is the infinitesimal version of your uh, intervals, but you can obviously write the finite version. So for finite version, it just delta t square minus delta vector x square must equal to del c square delta t prime square minus delta x prime square. Okay, so this is a finite version. You can convince yourself that if it is true for infinitesimal version, then this is true for finite version. Okay, it's straightforward. Okay. Now let us ask the following question: can we construct a frame in which two events can occur at the same spatial point? It means that we have two events. Suppose we have two events, okay, P1 and say P2. Okay, so in this frame, these two events occur at two different spatial points. Agree? If they are occurring at same spatial point, then this question cease to exist. Okay, we assume first that there are two events, okay, and they are occurring at two different spatial points, x1 and x2. Now, is there any frame, say k prime, okay, in which these two events occur at same spatial point? Okay. So answer, you can find the answer in the following way. Okay, what we want a frame in which two events occur at the same spatial point. So now you consider this expression, okay, c square delta t square, okay, minus delta x square, delta x is vector x2 minus vector x1, is equal to this quantity c square delta t square minus delta x prime square. Now we want a frame in which these two events occur at the same spatial point. Okay, that means in prime frame, delta x prime must be 0, right? So I should equate this with c square delta t prime square, right? When this kind of frame exists, when we can do this kind of thing.
When the quantity on the left hand side will be greater than 0.
Okay. So let me let me change the this thing. This is there. Yeah. So yeah. So this quantity. Yeah. No change is required. I think we are already. So it is just a point that we can write this as minus this plus this also. Okay. Nothing will change if I write minus this plus, but I don't have to do that. Okay. Yeah. So now the question is, when such a frame exists. Okay, when see this quantity is square of something, so this is always positive. Okay, that means this quantity is also positive. So for events such that S12 square, this is nothing but your interval, right? S12. So S12 square, if it is positive, for events like these, okay, there exists a frame in which spatial separation is 0. Okay, so for events like these which satisfy this, okay, there always exists a frame in which you can make the spatial separation between these two events 0. Okay, so all the events in space time satisfying delta S12, sorry, delta satisfying S12 square equal to is greater than 0 are called Hello?
Yes, sir.
Yeah. So let me start again the video. Oh, it is already starting. Okay, fine. Okay, so there was some problem with the internet. Okay, so all the events in space-time satisfying S12 square
Yes.
greater than 0
Excuse me,
are
sir.
called.
You are not visible.
So the screen is not visible?
No, sir.
No, sir.
So
Okay, now is it visible?
Yes, sir.
yes, sir.
Yes, sir.
Yes, sir.
Okay. So all the events in space-time satisfying this are called time-like events. Okay, clear? Similarly, we can ask the question number 2, can we find a frame in which two events occur at same time, or you can say simultaneously. Okay, so this is the question. Okay, so again you equate c square dt square minus dx square, or let us write finite version of it. Okay, c square delta t square minus delta x square is equal to two events. Now they occur at same time. Okay, that means delta t prime must be 0, right? So it must be equal to minus delta x, sorry, delta x prime square. Okay, so when this can happen, if this is always positive, so minus, so right hand side is always negative. So if this is less than 0, it implies that for events satisfying S12 square less than 0, okay, we can find for such a events, we can always find a frame in which these two events can be made at same time. Okay, here. Okay, so these events, okay, are called, okay, so all the events satisfying these are called space like events. Okay, fine, clear. Okay, but now the way we constructed, the way we defined space like and time like, okay, we define them through the invariance of the interval. Okay, and the invariance of the interval means it is coordinate independent concept, right? The invariance of interval implies that interval in one frame is same as interval in another frame of two same events. Okay, agree? That means this classification is coordinate independent. Okay? It means that this implies that nature of event nature of events, namely time like and space like, is invariant concept. So if two events are space-like in one frame, they remain space-like in any other frame. Okay. If two events are time-like in one frame, they remain to be so in any other frame. Okay. They will not change their characters. Okay. So if two events are space-like separated, they will remain space-like separated, because in other what goes wrong if two events are space-like in one frame, and uh, those two same events are time-like in another frame? What will go wrong? It means that this is not this the interval square, or this S12 is not invariant. Okay, is that clear? Okay, see the way we defined this space like and time like intervals. Okay, it is through this invariant distance, or invariant intervals. Okay, we use that crucially here. Fine. So what? Note that I have not yet found out the Lorentz transformations. Okay. Before finding the explicit form of transformations, we are deducing whatever is possible. Okay. Clear? So the classification of events into space-like and time-like is invariant in nature. Okay. Yeah. And obviously dx square equal to 0 is another type of characterization, another type of classification. It's called null events. The events for which your interval is 0 are called null events. Okay, so we have space like, we have time like, and we have null events. Okay, clear? Now let us concentrate on time like events. Let us concentrate on time like events. Okay. Let us concentrate on these time like events. Okay, so I will first draw this space-time diagram. Okay. So this is your CT, and this is, say, X. I can write vector S, but let us consider only one spatial dimension. Okay. So now you have, suppose I have two events which are time like separated. Okay, firstly let us consider two events or series of events which are null separated. Okay, so I have a origin here. Okay, let us consider another event which is null separated from this. It will be, where it will happen? It will happen on the line ct equal to x, right? That means c square t square equal to x square, right? Okay. So on this line, the line which is at 45 degree, okay, this line represents series of events, okay, which are null separate. Okay, series of event, I mean, take any point on this. Okay, separation of this event, separation between this and origin is null. Okay, take any other point, separation of this point and origin is again null, and so on. Okay, so I can extend this backward also. Okay, but it is not the only solution. You want c square t square equal to x square, right? So I am showing here one dimension, even there also I can have this line, because t can be ct can be minus x, so I will have this line. Okay, and I can extend it back. Okay, so I have plus ct equal to plus x and ct equal to minus x. Okay, now
Sir,
consider any two. Yes.
sir, what is this? Does this null event physically signify?
They signify the travel of light, electromagnetic signals. Okay, this is what we first discussed at the beginning. Okay, for them ds, your s12 is always 0. Okay, so it is sending and receiving the light signals. Okay, clear? So the event p1, which is the event of sending the light signal, and event p2, they must be null separated. Okay, clear? Okay. So we have here the space-time diagram in which this line ct equal to x represents null separated events, and similarly this line also null separated events. Okay, now consider any two events here. Okay, consider any two events in, say, okay, let me denote this as region 1. Okay, this thing, this region as region 2. Okay, this region as region 3, and this is region 4. Okay, and now let us discuss these regions one by one. Okay, fine. What will happen to, okay, let us consider any one event in this region 1. Let us consider event here. Let us consider event p. Okay, so in region 1, okay, what is going to happen? The region 1, any event this p, okay, is time like separated from event o, origin. Okay, this is your origin o. Okay, so any event inside this region 1, okay, is time like separated. Okay, because ct, okay, c square t square is greater than x square. Okay, so what are the coordinates of origin? It is p equal to 0, x equal to 0. Okay, so c square t square minus x square is greater than 0. Okay, that means this p is time like separated from o. Okay. Now can you find a Lorentz frame in which, okay, so this t here, what is the sense of t? T is increasing. Okay, as we go from origin, okay, upwards, t keep on increasing. Okay, so can you find a frame in which you can make this t positive to negative? Suppose we are in this region. Okay, suppose we are in this region. Can you go from this region to this region? Here it is t is minus t, right? This is minus t direction. This is plus t direction. Can you go from this to this? See, going from this to this would involve what?
Traveling at infinite speed.
No, I'm not crossing. I'm not. I don't have to necessarily cross here, right? I can come here and I can go here, right? Hmm? So what will, this is the only thing, but what will violate by doing that? See, one thing is that we have to,
Causality.
no, not causality, not right now. See, if two events are time like in one frame, they remain time like in any other frame. But what happens here? Okay, they we are making them simultaneous, right? Okay, if two events are time like, okay, if if O and P are time like, they should remain time like in any Lorentz frame, in any inertial frame. Okay, so this will forbid going from here to crossing this line as well as touching the origin. Okay, is that clear? Okay, so you cannot find a frame in which you can make t to minus t. Is that clear? Hmm? So these, the events which are occurring here, okay, suppose this event is occurring at time say t equal to 5 seconds, okay, and this event at origin is occurring at t equal to 0 second. Okay, this uh, this difference between them, okay, is always positive, and it will remain positive. That order, the difference might increase or decrease, okay, but it will never goes to zero. This is what it says. Okay, t of origin is 0, and suppose this t of this point P is say 5 seconds. Okay, it means that point P will always remain in future relative to O, always remain in future time relative to O. Okay, is this clear? Okay. This point P event inside this region 1 are always in future relative to event at O. Remember, we are talking relative to O now. This is the space-time diagram centered at O, not any other event. Okay, it is the we are talking everything relative to this event. Okay, so all the events in region 1 are in future of event at O. Similarly, all the events in this region, region 2. So let me say, so it implies all the events in region 1 are, all the events in region 1 are at future time relative to O. Okay. Similarly, in region 2, what is happening? What can I say? Suppose if I consider any event, say P, then all the events which are happening inside this region 2, okay, they will remain in future past of this event. Okay. Same argument you can go. You cannot go from here to here now. Okay. So all the events in region 2 are in are in are past are past events relative to event O. Okay. So these regions, there is an absolute concept of future and past. Suppose you concentrate on region 1. Okay. In this region, there is an absolute concept of future. Okay. So two events, if they are separated, if two events are such that T1 is greater than T naught, here T naught is 0, then this T1 will always remain greater than T naught. Okay, so instead of 0, suppose if I write T naught here, then any event here will be such that T of that event is always greater than always greater than T naught. So there is sense when we talk about uh, when we talk like event P is occurring after event O. Okay, it makes sense, right? When any event in region 1 occurs after O. Similarly, any event here occurs before O. Okay, so there is a sense when we talk future and past in these regions 1 and 2.
Sir,
Huh?
sir, in both region 1 and 2, for this time-like events, there is the condition that delta S square is greater than 0 for both region 1 and 2, right, sir?
Hmm.
Sir,
Yes.
but so, sir, and sir, we are invoking only this condition, right?
Pardon?
For and sir, we are considering only this condition currently
Yes,
to
yes, yes.
estimate whether the one event P can cross over to region 2.
Yes,
Uh,
yes.
but sir, in both these regions, that condition is satisfied.
Correct.
So,
So it will satisfy.
yes, sir. So still we are saying that you cannot cross over from region 1 to
Yes,
region
but
2.
because then I have to cross here, right? In this region, to go from here to here, what do we need to do? Okay, we need to cross either from the origin or we have to cross this line.
Yes.
Taking this
Mhm.
point from here to here, what it
Yes.
means. Okay, you in somewhere you have to make you have to construct a frame in which both the events occur simultaneously, right? That frame will
Mhm.
come in. Okay,
Yes. Yes.
correct. Okay,
Yes,
so
sir.
it should not happen. It should not happen. That should not
Yes.
happen. Okay, fine. Okay, now is this clear? Okay, so in these regions there is a notion of absolute future and absolute past. Okay, so this is absolute future and this is absolute past. Okay, now you can imagine what should happen here in the region 3 and region 4. Okay, in this region 3, okay, two events can occur simultaneously. Okay, suppose I have two events, so let us go to next page. Okay, so I will again draw space-time diagram, this time in a slightly different way. I will draw, for a convenience, I will draw this three-dimensional figure. It will be better, just to illustrate what is happening. So let us concentrate only on the future. So in three dimension, it will be like this, right? So in last diagram, we only had one dimension, one special dimension. In three dimension, it will look like this. Okay, and now we have uh, this region. Okay, so similarly, there will be something like this. There will be a cone. Okay, okay. So we discussed region in this region here and region here. We discussed about region here and region here. This is 1 and 2. Okay, what happens in region 3? Okay, You consider any two events here. Okay. Suppose they are separated in time by amount delta t. Okay. Suppose these events are separated in time by amount delta t. Okay. I can always find a frame in which I can make this delta t root 0. Okay. Right? This is the question we asked here. Okay. Can we find a frame in which two events occur at the same time? Okay, and these events are characterized, are classified as space-like events. Okay, so I can always, for events like these, I can always find a frame in which delta t is 0. On top of that, I can always find a frame in which delta t is negative also. Then, right? Clear? Okay. If delta t is 0, if I can make delta t 0, I can make delta t negative also. So there is no notion of future and past here. If the events, suppose if someone is talking about this event P, okay, so let us formalize this. Okay. So let us consider this event O, and let us consider any other event, say P, in region 3. Okay. So this event at origin and this event at point P. Okay, they are space-like separated. Okay. Suppose delta t in this frame, delta t is greater than 0. Okay. The point is that I can always find a frame K prime in which delta t for same event P, okay, delta t is 0 or delta t is less than 0. Why is that? Because now see, in 3 dimension, we don't have to cross this cone. Okay, you can come here, right? Clear? You can go from here, in fact you can do even better. You can go from this point to this point. I don't have to cross this cone. Imagine a figure in 3 dimension. Okay, in 3 dimension, if you draw in appropriate manner, so it will be like these are the hyperboloids. Okay, I will be having these hyperboloids like this. This is how you make cone, right? Okay, and there will be origin. Okay, so imagine this figure in 3 dimension. Okay, I can go from point this to this point to this point. Okay, clear? Without crossing this cone. Hmm? Is that clear? Okay, so there is no notion of future and past in region 3 and in region 4. In fact, there is no region 4 actually. You can talk, there are only 3 regions. What are those? Region 1, region 2, and whatever remains is region 3. In 3 dimension, you can convince yourself that there is region 1, there is region 2, and whatever remains outside this cone is region 3. And outside the cone is space-like, is the region of space-like events. Okay. So for in this region, there is no notion of absolute future or absolute past. Okay. So we should not
Sir,
talk about ordering, time ordering. Yes. Yes. There
in
was
the
a
region
question.
3, what we get is that c square dt square.
Uh,
In the region 3, c square dt square minus dx square is less than 0. So c square is less than dx square by dt square.
No, 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 no. C square. What? No, 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 no. C square is not less than ds by dt square. You have c square t square in this region. Okay, c square delta t square is less than delta x square. It does not mean that c square is less than.
Can we put the delta t to the denominator?
No, 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 no. But see, c is constant, right? See, this is the line. Okay, you are talking about the events. You are talking what you are changing. You are changing the events, right? It is a change in the events. Clear? Okay, you imagine this. You go to your interval. Okay, how you write the interval? Interval S12 is S12 square is C square delta T square minus delta X square. Okay, clear? If suppose this interval is 0, does that mean that C equal to 0? If suppose this is 0, okay, suppose if I say this is equal to 0, then square delta x square by delta t square is equal to c square. Okay. This would mean that we are traveling at the speed of light. Okay, this is when you say this is the meaning that dx by dt is v, which is c. That is the meaning. Okay, clear? Similarly,
Sir, similarly, if we
what do you want to say? If suppose if delta x square, so if suppose this is less than 0, okay, then delta c square is less than. It does not mean that c square is, see, you have to say that the velocity of the particle in this region, okay, if you consider velocity that is greater than c square, that you can say. Okay, it means c square is less than delta x square divided by delta t square, right? Okay, imagine this as some kind of velocity. Okay, so it is velocity square. So in this region, if you had any particle, that would travel faster than light. That is what it means. It does not mean that c square is less than 0. Agree?
so means this region is not possible.
For material particles, it's not possible, but that is different story. Okay, fine. Okay, but it does not mean that c square is less than 0. Okay,
No,
if
sir.
we had any particle in this region 3, then its velocity is always greater than c. This is what it means. Physical, not physical, that it's not yet. We are not making any statement about that. Okay.
So if the
If there is
particle has
any,
velocity greater than c, then only it can travel through the past.
yes, but we are not making any statement about that. Okay. What it means is, what we are saying is that if there is any particle, okay, in region 3, then it will travel greater than c. If there is any, okay, we'll see what happens to that. Okay, but it does not mean, certainly does not mean that c square is less than 0. Okay, fine. So the important thing is, you can, in this region, you can go from t greater than 0 to t less than 0. I can always find a frame in which I can change the sense of time. So there is no for if, so it implies for region 3 and 4, no notion of future, public past, absolute future. Absolute future, absolute past. Okay. Okay. In fact, we can make stronger statement. There is no ordering, no time ordering. You cannot order events according to time. It's very important. Okay. You cannot see in this region, in region 1, if I give you series of events, okay, then you can order them with time, and that will remain fixed. Okay, but in this region, okay, You cannot do that. Okay, fine. Okay. So what is the time? Let me take good. Okay. So now let us consider, let us go ahead with this and let us consider two frames, frame K and frame K prime. Okay, and you have frame K which is at rest.
Sir, what about the null?
Null is the boundary. Null thing is the boundary. Okay, it is the no specific thing happen.
So
it
they
is
are
just
ordered in the time.
No, for them there is nothing, right? So it is ds is equal to ds square equal to 0. Okay, they are very special case, special character. So it is it is a light waves. Okay, you have a light waves which are spreading outward, you have light waves spreading inwards. Okay, no special thing, no characterization can be given here. ds equal to 0 based on this. Okay, because here delta t, what will happen? So ds square equal to 0. So c square delta t is square is always equal to plus or minus c delta t. C delta t is always equal to dx mod. Okay, so this is by definition, it is if in this thing it is always positive and this thing also always negative. Okay, by construction here, okay, this delta x is always positive. Okay, and here also magnet of delta x is always positive, and here the magnet of delta x is this quantity will be negative and this quantity will be negative. Okay,
Sir, what comment we can make about the time ordering in the null, on the null line?
time ordering you can always make, right? So that notion ceases to exist because it is related to x. So if you have delta x, suppose you have delta x here, suppose this is your delta x, and you suppose this is delta x1 and this is delta x2. Okay, if delta x1 is greater than delta x2, hence delta t is greater than delta t. Delta t1 will be greater than delta t2. That is inherently taken into account. It's automatic because it is, we are on the line. Okay, this event will intersect here. This will intersect here. Okay, so obviously this thing delta t, okay, will be less than this delta t. This will remain as it is. Okay, but it is trivial because this is because there are no there is strict equality here, so there is no special case. Here we had inequalities. Okay, there is equality, strong equality is there. Yeah. Yeah. So if two events are there which are null separated, okay, they will remain null separated. Okay, clear? Obviously, their time ordering will be followed because there is equality here now. Is it clear? So now consider two frames, K and K prime. Okay, and let us consider a particle, okay, which is moving in this frame. Let us consider a particle moving in arbitrary manner, okay, in this frame, okay, in K frame, okay, and let its instantaneous velocity be v, instantaneous speed be v, say u. I can put v. Let us put let it be v. Okay, fine. So the observer in K frame, what it sees in time delta t, in time dt, okay, this particle is going to move by distance, say dx square plus dy square plus dz square. square root. In time dt, okay, this particle is moving along this trajectory. Okay, so this particle will move distance will be moved by this distance. Okay, clear? Okay. Now suppose if I take this k prime frame, okay, and attach, so suppose this is my particle. Okay, I will take this my k prime frame and attached on this particle. Now this is my k prime frame. Okay, clear? And now the question is, what is this time interval dt? What can I say about, see, once I attach this k prime frame on the particle, relative to that k prime frame, this particle is at rest, right? Because this frame will always be there with the particle. Okay, so relative to that k prime frame, this particle is at rest. So dx prime, dy prime, dz prime will be 0. Okay, so if in the k frame observer note this time difference dt, okay, for a particle to go from to travel distance this much, then what is this observer will see? What this observer in k prime frame will see? In other words, what is the observer sitting on the particle will note? Okay. What time interval this observer on the particle will note? That is the question. Okay, but it's very easy to answer. Once we have this invariance concept of invariant intervals, it's easy to answer. Okay, so what you have to do is you have to equate c square dt prime square, okay, to, because dx prime vector will be 0, because related to that frame a particle is at rest. So you have to equate this with, okay, in other words, dt prime will be equal to dt into, so if I divide dt here, so it will be and c square if I divide, so I will take c square this thing common and I will cancel, so it will be 1 minus dx by dt is v, so it is v square by c square. Okay, fine. So what is the conclusion? Note that this particle is not moving in a uniform, is not moving uniformly. It may, at this state, this particle can move in arbitrary fashion. Okay, instantaneously you can thought that this particle is in uniform motion instantaneously. Okay, and suppose this instantaneous velocity is v, so we can imagine two frames which are moving instantaneously with velocity v. Okay, then the time interval observed by one frame dt prime is equal to dt with multiplied by this factor. Okay, this is the time interval observed by this is time interval as per the observer at rest, and this is the time interval as per the observer moving instantaneously with velocity v relative to this frame k. Okay, clear? Okay, so you can see, because this v is always less, since this v is always less than c, okay, now you consider the material particles moving with velocity which is less than c. Okay, and obviously that is the limit. Okay, dt prime, okay, since this v is always less than c, dt prime is always less than dt. Okay, is that clear? Okay, and the shortening factor is this. Clear? Okay. Now, for this is the infinitesimal time interval. Okay. If you want to calculate finite time interval observed in frame k prime, then you have to just integrate it. Okay. Then you will integrate this from t1 to t2 dt, okay, 1 minus v square by c square. But I cannot take this factor out of the integral because v may depend on t. If it is uniform, then and only then I can take this factor, I can pull this factor outside. Okay.
Excuse me, sir.
Yeah.
Sir, since our main postulate for relativity was based on the fact that the relative velocity between the two frames must be the same. But in this case,
yeah.
So when we are now talking about the finite time difference, we are now also including v as a function of time. That means we
Yes.
are now.
So I cannot. Now that means I cannot do anything here unless I know what kind of function I am talking about. But this statement, see, this statement is about the instantaneous relation between instantaneous interval, instantaneous velocity. Okay. Here, when I say v here, it is the instantaneous velocity between two frames. So whatever the postulate about relativity, that will hold instantaneously, right? It will always hold. So I can make this statement always. Okay, I can integrate this always, provided I know this function of v, how v behaves as a function of time.
Okay, sir. So in the integration, sir, in the integration thing, we are permitted, means it is mathematically permitted for v to be a function of time. Means it can vary.
Yes. Obviously.
So, yes, sir. So means that in this finite time difference case, when integration, that velocity between the relative frames may vary, may be a function of time. So
yes. As far as this formula is concerned, yes. See, I'm equating these intervals. Okay, how I got this by equating the by using the invariance of intervals. Okay, that I did instantaneously. Okay, and then I integrate it. That is always possible. Why not? It is possible. It is always possible. Okay. Clear? Okay. I can always do this thing, provided I know this function. Now the point is that it may not see, this is nothing but your in a way this is nothing but your Lorentz transformation. Okay, when I put v equal to uniform, I will get the Lorentz transformation, uniform motion. Okay, when I consider v to be uniform, I will get a Lorentz transformation, your familiar Lorentz transformation. Okay, but this I can always make, this statement I can always make. Okay, because see, instantaneously, let us consider this. Instantaneously, I can always consider a frame which is moving uniformly. With suppose this is frame k double prime. Okay, this k double prime is moving with velocity, say v some v2. Okay, relative to this k. At that instant, this equation holds always. Okay, and when you integrate it, everything is taken into account. Okay, how v behaves as a function of a, according to that you will get the answer. Okay.
yes, sir.
Okay. So now, as a special case, suppose v is constant, then t2 prime minus t1 prime is equal to 1 minus, I can pull this factor outside of the integral, half, and T2 minus T1. Okay, so this is nothing but, see, this factor is always less than 1. Okay, so T2 prime minus T1 prime is always less than 1. Okay, this is nothing but your moving clocks as observed by the rest of, as observed from the rest frame. Okay, okay, lags behind. Okay, so T2 minus T1 is the interval between the events, time interval between the events as observed from the rest frame, and T2 prime minus T1 prime is the time interval in moving frame. Okay, this time interval is always smaller than this. Okay, that means this clock as seen by moving observer, okay, is uh, it run faster than it is than in the rest observer, than related to rest observer. Okay, this is what it means. Clear? Okay, but we don't need a specific form of Lorentz transformation. That is the misconception. You need the specific form of Lorentz transformation to observe this time dilation. This is called time dilation, right? We don't need that. We are just assuming that V is constant. This is the general transformation. This is the most general thing which you can say. Forget about this. Okay, this is the most general thing you can say. Okay, this statement. Okay, in this now you put V to be uniform. Uniform V independent of T. Okay, then you can integrate easily. Factor a constant factor. It's just T2 minus T1. Here you will get T2 prime minus T1 prime. Clear? So the time interval. So what is the conclusion? Conclusion here is the time interval indicated by moving clock. Okay, is always smaller than the time interval indicated by rest clock, clock at rest or observer at rest. Okay. Now the next thing, okay, let me see what is the time. Time is almost 2, but let me go further. Okay. So I will denote this quantity notationally. In future we will denote this quantity 1 minus v square by c square minus half, that is 1 over square root of 1 minus v square by c square by gamma. Okay, this is our notation. And there is another notation, v by c is beta. Okay, so these are the two notations. Okay. Nothing is, I'm just relabeling it. No new thing. Okay, now consider yeah, so just a minute. Yeah, now consider the specific, what are these exact transformations between frame K to frame K prime. Suppose I have frame K, okay, and I have frame K prime which is moving with velocity v in x prime direction. Is x prime, x, y, z. Okay, this is y prime, z prime. Okay, and this K prime frame is moving in x prime direction. So all these x's at t equal to 0, they are coincide. Okay, the origin of K prime is coincides with origin of K prime frame, and all the axes are parallel to each other. Okay, and I'm giving a velocity to this frame in x prime direction. Okay, velocity is v. Okay, now what are these transformations? What is the form of transformation which takes me from this frame to this frame. Okay, that is what we need to find out. Okay. Now, after discussing this invariance of the interval, okay, the derivation of Lorentz transformation is quite easy now. Okay, just a bit. Okay, let me put my laptop in charge. Just a minute. Okay. So we have two frames, x, y, z, t, and x prime, y prime, z prime, t prime, and at t equal to 0, they both coincide. Their origin is origin of these two frames coincide. Okay, and we want the relation between them. We want the relation between this frame to this frame or this frame to this frame. It doesn't matter. Okay. Now, what that relation could be? Okay. If I now I have discussed the invariance of the interval. Okay. So, okay, let us go to your R3. Okay. In three-dimensional space, okay, suppose I have two frames, and this is another frame. This dotted is another frame. Okay, so dotted lines represent prime frame, so it is x prime, y prime axis, and this is y and x. How you derive the relation between these two frames? Suppose there is one frame and I construct another frame by rotation by an angle theta. Okay, this rotation will not change the distance between, like I said before, this r square will remain same, right? R square in one frame and r square in rotated frame is not going to change. You use this fact and you derived this x y equal to cos theta minus sin theta cos theta. I hope you know this. X prime y prime. Okay, or x prime y prime equal to, you to just change theta by minus theta. Okay, then you will get cos theta sin theta minus sin theta cos theta. So I should write here x prime y prime, x and y. Okay, these transformations will not change this distance of any point from the origin. That means this quantity remains unchanged. X square plus y square equal to x prime square plus y prime square. Right? So because of this plus sign here, you have these trigonometric functions. Okay, because essentially the cos square plus sin square is 1. That is what is being used. Okay, but now we have minus sign. Okay, okay, and let us since our k prime frame is moving along x prime direction. Okay, there is no change expected in perpendicular directions. Okay, you can convince yourself that If there is any change, then it will violate your suppose if I'm giving the velocity along x prime direction, and if I expect that there is a change, y is going to change, it would mean that you are giving this frame or this frame a special importance. You can distinguish between two frames. If I'm giving velocity in this direction, and if I expect y or z to change, then that expectation, okay, will lead to giving preference to either this frame or this frame. You can convince yourself. Okay, you use the same logic which you used before, this isotropy and homogeneity. Okay, so we expect change to occur only for x coordinate and t coordinate. Let us see how. Okay, so we want to keep what we want to keep. We want to keep this element c square t square minus vector x square to be same in k prime and k prime prime. Okay, fine. And for simplicity, let us consider only x. Instead of writing vector x, I will write only x. Okay, so my transformation would be such that c square t square minus x square is equal to c square t prime square minus x prime square. Clear? Suppose if I consider by making analogy with the rotation. Okay, suppose if I assume x equal to, okay, if I assume x equal to x prime, instead of trigonometric function, if I assume hyperbolic function, cos hyperbolic, say cos hyperbolic of some angle, say phi, okay, plus y prime, sorry, I should write t here, right? It is a t here, plus c t prime sine hyperbolic phi, okay, and ct is equal to x prime sine hyperbolic phi plus ct prime cos hyperbolic phi. Okay. You will know why I use these hyperbolic transformations, hyperbolic functions. Okay. Okay. So this is x. I don't know yet what is this angle. So finding the transformation means finding this phi. Now, okay. Clear? Suppose we concentrate on the motion of the origin. Okay, let us concentrate only on the origin. Okay, what is going to happen relative to this k frame? Suppose if I am trying to observe the motion of this origin, what is going to happen in this transformation? What should I do? Okay, if I want to know the what are the transformation for this point origin, how this point is transformed into k frame, if I want to know that, what should I do? I have to put x prime equal to 0 here. Yeah, okay. So if I put x prime equal to 0, what is going to happen? X equal to ct prime sine hyperbolic phi and ct equal to cos hyperbolic ct prime cos hyperbolic phi. Okay, it means take the ratio, so it is v by, so yeah, it is x divided by ct equal to, so t prime will go ct prime, x by ct is tan hyperbolic phi. Okay, it implies that x by t is nothing but the velocity of this origin, right? Okay, So it is V, velocity of the origin is nothing but this relative velocity. Okay? It is V by C equal to tan hyperbolic phi. Okay, so phi is essentially tan hyperbolic inverse of V by C, but V by C is beta. Okay, but anyway, I am not writing this bit in the form of beta. Okay, now you can use this. Okay. This means the following: you have this, the tan hyperbolic phi equal to V by C means sine hyperbolic square phi equal to V by C whole square into cos hyperbolic square phi, right? Because tan hyperbolic square will be V by C whole square, but it is sine hyperbolic by cos, so it will be sine hyperbolic phi equal to V by C whole square cos hyperbolic. Okay, so this implies what? This implies that cos hyperbolic, what will be cos hyperbolic? So it will be, you have sine hyperbolic square sorry, cos hyperbolic function, cos hyperbolic square phi minus sine hyperbolic square phi equal to 1. Okay, so from this you have cos hyperbolic square phi equal to cos hyperbolic square phi, okay, into 1 minus v square by c square, okay, equal to 1. In other words, your cos hyperbolic phi equal to 1 divided by 1 minus v square by c square square root. Okay, in other words, this is gamma. Okay, so cos hyperbolic phi is gamma. This implies sine hyperbolic phi is v by c times gamma, so it is beta gamma. Okay, so your transformations are now x equal to, go back here, so x equal to x prime. So we have found out what is this cos hyperbolic phi and sine hyperbolic phi. Okay, and this phi will remain same. See, this phi will be independent of t prime and x prime, so it doesn't matter what I choose origin, but it doesn't matter, for it will remain so for any other point. Okay, so this cos hyperbolic phi is gamma and sine hyperbolic phi is beta gamma. Okay, this means your x is equal to gamma x prime plus beta gamma t prime, and your ct prime is equal to uh, beta gamma x prime plus gamma ct prime. Okay, so this is nothing but your x is equal to gamma x prime plus beta t prime. Okay, beta, there is c somewhere. Let me see the c somewhere. There is a c here. Okay, sine hyperbolic is beta gamma, so c, so I missed it, c, so c is there. Okay, fine. So this is your x prime. Let me check. So it is c t prime, sine hyperbolic is beta gamma. Okay, so x is equal to gamma x prime plus c beta gamma is common, that is correct. So this is beta is 1, yeah, correct. Okay, and your t prime is equal to gamma, okay, gamma, okay, and it is beta by c, it will be beta by c, okay, x prime plus, because there was c here, so I divide by c, so beta by c x prime plus t prime. So these are, sorry, it should not be t prime, it is t. So these are your familiar Lorentz transformations. So you can invert it now and write it in terms of x and t. For x prime, you can write, just change v2 minus v. So if I change v2 minus v, gamma will remain unchanged and beta will change the sign. Okay, so it will be gamma into bracket x minus c beta t, and t prime will be equal to gamma. I will write this t prime first, t prime minus beta by c x prime. So yeah, correct. Okay, so these are your Lorentz transformations. Okay, is this clear? These are, I think this is, it's not new to you. Okay, these are Lorentz transformations, but I think you must have derived it in slightly different manner by using this geometric method, by light rays and all those, doing all those things, train and distance traveled by train and so on. Okay, why I have used this transformation, okay, cos and sine, why I use this hyperbolic function instead of trigonometry, okay, is because of this minus sign. Okay, so if I use this here, you can check that this remains same. Okay, if I put this thing here, indeed it remains same. Okay, if I put this x and ct here, you will get this, and that is because of this minus sign. Okay, so I think I will stop here, and then in next class we'll continue with discussion of special relativity. We will discuss the length contraction and the composition, the addition of velocities and so on, 4 vector and so on. Okay, so I hope you know about the composition rule of velocities, this Doppler effect. Do you know that? Doppler effect in relativity, aberration of light. Is it, has it been done already at the BSc level?
Yes, yes, it's done.
So it is done. So I will, maybe I will not skip that, but I will do it in, I will do it quickly. Okay, and then we will discuss about the 4 vectors. Okay, and there I will spend some time about the 4 vectors and tensor notation. Okay, in meantime, you try reading this Jackson's book. Okay, there is a one chapter special theory of relativity. I'm using the same notations as given by him. Okay, so you try to go through the Jackson's special theory of relativity chapter. Okay, I'm covering this from Jackson's book. Okay. You can use Landau and Lefschetz also. There is a Landau and Lefschetz volume 2, okay, classical theory of fields for special relativity. It's an excellent textbook. Okay, you can use that also. These two textbooks, Landau, Lefschetz, and Jackson. Okay? This we will be following for at least next 5 or 6 lectures. Okay, so I will stop. Okay, and next class will be on. So today is Monday. I will take next class on Wednesday. Yeah, Wednesday will take the next class. Okay, the same time. So the timetable will be same, right? On Wednesday also you don't have anything before AQM class on Wednesday.
No, sir, we had a lecture today, but it got postponed to 3:30.
So whose lecture?
We had a lecture at 11:15.
ED.
No, but which subject?
Kodekar, sir, AD2.
Oh, AD2. Okay, so but on Wednesday it will be there, right? In the timetable, is it there?
I think we have MM. We have
MMP. MMP2 we can. I will take tomorrow, and then I will take on Thursday. So MMP2, don't worry about MMP2. So I may not take tomorrow also. I will start MMP2 on Thursday. Okay, Thursday, Friday I will take MMP2. Okay,
Okay,
and
sir.
Monday and Wednesday I will take advanced quantum mechanics, and possibly on Saturday. Okay, so Monday, Wednesday, and Saturday I will take AQM, and Thursday, Friday I will take this MMP2. Okay.
Okay, sir.
Okay. So we'll meet on Wednesday, and but the problem is at MMP2 time there will be crystallography class. So is there anyone who has taken crystallography and AQM?
No, no, sir.
Those who are attending
No.
AQM class, they're all in MMP2, right?
Yes,
Yeah.
yes.
So yeah. So then I can take AQM class at least. Okay. I cannot take MMP2 for 1.5 hours because of these other classes, but I can take this class, AQM class, for 1.5 hours or 2 hours, right? On Wednesday. Hmm? Okay, then
Yes, yes.
stop the recording and then